Okay. Also, if you're online and you have questions during the talk, feel free to write them in the chat, and we'll answer them at the end, or just raise your hand either way. So we're happy today to introduce Julia Sisk. So Julia is a third-year PhD student at the Institute of Astronomy at University of Cambridge, UK. And she's working under Professor Chris Reynolds and Dr. James Matthews. In the summer of 2020, Julia graduated with a first-class integrated master's degree in physics from the University of Manchester, where she worked on predicting the thermal
Sunyaev-Zel'dovich effect.
Thank you. From analytic cluster pressure profiles. She grew up in the islands off of Spain. And since the start of her PhD, Julia has been focusing on understanding how current and next generation X-ray missions can help us probe very light Axion-Like particles. And as a side project, she also sets constraints on one of the most massive, supermassive black holes. The spin has been constrained via X-ray reflection. So today, Julia will be talking to us about using the hot and energetic universe to constrain Axion-Like particles in black hole spin. So with that, thank you for coming, and take it away.
Thank you. So thank you, Amy, for the introduction. Today, I'll be talking about how we can use the hot and energetic universe to constrain Axion-Like particles and black hole spin. And hopefully, I'll be able to convince you that this is an exciting part of science, and there's still a lot to be done. So for my talk, I'll be firstly talking about axions and axion-like particles, why they are important in the theory. And then I'll be mostly focusing on presenting the tightest constraints to date that we found for very low mass axion-like particles from a Chandra observation of a very luminous radio-quiet quasar, which is H1821+643. And then I'll be talking to you about what we hope to achieve in the near future with the next generation X-ray observatories. So I'll be taking simulated observations of NGC1275, the central AGN at the Perseus cluster, and explaining what Athena and Axis will be able to do. And then finally, I'll be highlighting the exciting spin constraint that we found for the high mass supermassive black hole at the center of the 1821+643 quasar. So in terms of the axion part of things, I don't think I need to motivate the recent interest in astrophysical axion-like particle searches too much. I think we also that over the last 2 or 3 weeks, the archive has been populated by the series of papers that were trying to link this extraordinarily gamma ray burst event with a tentative axion hint. And these are the parameters that they were getting at. And unfortunately, it seems that this event was caused by a very energetic cosmic ray. But I just want to highlight that with different wave bands, we can use astrophysics to access the parameter space of these particles. So this is something clearly very exciting. So to understand axion-like particles, we first must understand why the QCD axion was proposed in the first place. So as you may know, these particles were proposed in the 1970s, and they were named after a cleaning product, this Axion detergent. And this is because the QCD axion was proposed to clean up one of the problems of the standard model of particle physics, namely the strong CP problem. And the strong CP problem is the absence of charge parity violation in nature that clashes with the predictions of the standard model of particle physics. So in the standard model, we have this QCD Lagrangian term that is odd under charge parity symmetry. And the strength of this charge parity violating term is determined by this angle theta, which is a constant. And you should think that the value of theta favored by the theory is just 1. But however, experimental observations of the electric dipole moment of the neutron suggest that the upper bound on theta should be something that is consistent with 0. So the question is whether we can resolve this apparent tension without having a fine-tuning problem in the standard model. And the answer is yes, but we need beyond the standard model physics to do this. So this tension is resolved by something called the Pechaquin mechanism, which consists in replacing this theta term by a dynamically varying quantity. So we see in this expression for theta that I have at the top that we have this fraction here, A divided by FA, where A is a field, and FA is called the axion decay constant, and it allows us to conserve the units of A that make theta dimensionless, because theta again is an angle. So we see that this A, which is a field, has an associated potential, and there will be some point in time where A will be able to roll down the potential. So the potential will be at its minimum, which will enable theta to become dynamically zero. So what we have essentially done is to replace our CP violating term in the Lagrangian theta by a dynamically varying term A. And mathematically, we do this by introducing a new symmetry in the standard model, which is called the Pechaquin symmetry, that breaks spontaneously at the QCD phase transition. And as you may remember from particle physics, when we introduce new symmetries that break, we get new particles. So this is the QCD axion. And as we can see here, the QCD axion is expected to mix with electromagnetism. So this is something that I'll talk about later. And importantly, the products of its mass and its decay constant are set by those of the neutral pion. So for the QCD axion, the original axion that was proposed in the 1970s, we know the relationship that its decay constant holds as a function of its rest mass. But however, we have not detected the QCD axion. And now I'm going to start talking about axion-like particles that I'm just going to refer to as axions for simplicity. But this is a new class of particles that are generic predictions within beyond the standard model frameworks, such as string theories. And they are predicted to mix with standard model particles as QCD axions do. So for example, they mix with electromagnetism using the same Feynman diagrams that we saw in the previous slide. But however, their masses and couplings are no longer tied together by the theory. So the question is whether we can set bounds on F as a function of their mass. And in certain regimes, these are very strong. Yeah?
Yeah, sorry, I don't want to interrupt. But,
No, it's go ahead.
You said we haven't detected the QCD axion. Is the whole parameter space of energies ruled out, or is it just, no, we ruled out some part and haven't detected there?
Yeah, so the original QCD axion was proposed to be in a certain mass range. So I'm referring to the papers written by Weinberg and Wilczek in the 1970s. And we haven't detected the QCD axion in the KeV mass range using a series of laboratory experiments. But now, if we assume that axions are the cold dark matter of the universe, we know that they are favored because they resolve some tensions in the theory. So I mean, so for example, if we're talking about ultralight dark matter, we know that a type of ultralight dark matter is spotty dark matter, which is preferred in certain theory frameworks because we are able to solve problems such as the cost versus core problem. And here we're talking about rest masses of 10 to the minus 22 eV. But with the type of experiments that I'll be talking about, we know what couplings we could get of these particles to electromagnetism, but with observations, we cannot set constraints on the mass, if that makes sense.
And I mean, do these still solve the CP problem, or is it just?
Yeah, so generically, axion-like particles do not solve the strong CP problem. So this is because we no longer have this relationship between their masses and their couplings.
Right.
And following up from what you asked, this is just a representation of what different string theories predict for G, so this coupling that we'll be trying to constrain. And as you can see, different string theories predict different values of G to be favored within each of these frameworks. And this is starting to probe the parameter space that we can access with X-ray telescopes. So eventually, this suggests that in the near future, we might be able to test some of the predictions of string theories with these X-ray axion searches, which is very exciting. And well, I've already mentioned this slide, and unfortunately, we don't have any access to setting bounds on these axion masses with the type of searches that I'll be talking about. But this is just something to bear in mind, that in certain regimes, these ultralight dark matter models are preferred, and their impact, for example, on the cosmological history of structure formation in the universe has been studied and has been embedded in cosmological simulation codes such as ERICO. And this is something that Anastasia Fialkov and collaborators in Cambridge have been working on over the last few years. So the phenomenology of the interaction that we're going to be looking at is embedded by this Lagrangian term. So I've mentioned X-ray energy. So we're going to be talking about energies of orders of keV, which are much greater than the rest masses of the axions that we're trying to constrain. So we're constraining masses less than 10 to the minus 12 eV. And in this regime, the dominant interaction term for axions and photons is given by these. So we see that G is the parameter that is quantifying the strength of this mixing process, and A is our axion field. And then we have the dot product of the electric and magnetic fields, E and B. And importantly, the Feynman diagram that we're going to be considering is this one, where we have a photon being propagating through a magnetized and ionized medium. And if we're in a suitable location of parameter space, these photons will interact to produce an axion. So what we'll be trying to look at is at a region of parameter space where this Lagrangian will be non-zero. And we should be able to quantify this eventually into an observable that will refer to as a mixing probability of photons going into axions. And as you can see, if we are able to solve for this probability analytically, this is a very complicated process, and I've just assumed a suitable and simplified magnetic field configuration here. But what we can see is that this mixing probability for a given set of axion parameters is an energy dependent function. And this function also varies, you cannot see this, but this is the distance traveled by this photon beam before it mixes into an axion. So you can think analogously to neutrino oscillations, where you have a neutrino starting in a specific state, and then it travels through a path length, and then it has a non-zero probability of having mixed into another neutrino flavor state. But here what we have is an initial photon beam starting with the polarization state, and then it has a non-zero probability of mixing into an axion of a given mass and coupling as it travels through a magnetized medium. And of course, this induces energy-dependent oscillations or spectral distortions that we should be able to see in the spectra of point-like sources. So the idea is that if we cannot see these spectral distortions, then we can set bounds on axions. And yes. Yes.
Are these x-axes somehow like correlated with time? Are we talking about like the polarization changing as a function of time, or like why does it look like an oscillation but the x-axes are not? obviously time or monotonous?
Yeah, so this is a very good question. So because the idea is that these axions are sufficiently low mass, enough that this transition will happen instantaneously. So if we were talking about a different mass range, and in the specific process that we were considering, maybe time would have to be taken into account, but it's not embedded here. So what matters for this transition is essentially the strength of the magnetic field along the path that is magnetized, if that makes sense. Yeah.
I just have to think about it more. I guess I don't understand, like, it looks like an oscillation,
Yes.
right?
Yes.
But in what space? It's an oscillation of what?
Okay, so what we're seeing here is I think I understand your question, but it's in the space that is magnetized. So if we are assuming that the magnetic field is constant in time and uniform, what matters is the product of the magnetic field strength along the path length that the photon is traveling, where this magnetic field exists. Because and this is something that is captured by this Feynman diagram here. So our time variable becomes this path length, if you like. And this is for only a given path length. And this is for a given energy. So what we really have is this mixing probability being a very complicated function of the axion parameters that we're trying to constrain, the mass and the coupling, and the energy of the beam, and the path length traveled, and the plasma frequency of the background medium, or the electron number density in the plasma. And here we're assuming that our magnetic field configuration is uniform.
And what happens if the magnetic field, the strong magnetic field?
So if the magnetic field is not strong enough, so what we're trying to maximize is the product of B times L. So if the magnetic field is not strong enough, then this mixing probability will become suppressed. So in this regime, you would not expect to see energy-dependent oscillations due to photon-axion mixing, and you would not necessarily be able to use astrophysical sources to constrain these particles.
What about axion interactions with electric fields?
Yes, so
There are places where there are very strong electric fields. So is that another option?
yes, so I believe that this is the target of laboratory experiments trying to probe axion parameter space, and this can take you to slightly different mass ranges, which are starting to probe the realm of QCD axions, so the axions that can solve the strong CP problem. But this is something that we don't have access to doing with clusters of galaxies. Any more questions? So as you can see, we can try to look for these energy-dependent spectral distortions or modulations induced by this non-zero mixing probability and constrain axions in a very wide range of masses. And this allows us to build up these so-called exclusion curves. So the way these curves can be interpreted is as follows. So for example, if we're looking at the past results, I'm going to use the ruler here. So if we're looking at these results from past and we're talking about axion masses of 10⁻³ eV, then everything above the curve is parameter space for G that has been excluded at the 2 sigma or 3 sigma levels. So the idea is to find astrophysical sources that allow us to go further down, as deep down as possible, so as to expand the parameter space for G that has been excluded for a given axion mass.
Why are XMM Newton and Chandra on the opposite sides of the scale?
Yeah, so very good question. So this this study was not looking at the type of energy dependent distortions that we're talking about here. So this study was searching for axion dark matter using XMM Newton blank sky observations. So here we are talking about axions that are dark matter and are constrained, or their abundance is constrained by the fraction that they would represent over the fraction of dark matter. But here we are not making any assumptions on the nature of these particles. So we're really probing the realm of stringy axions, or the axions that could be produced by expected from string theories, down to masses below this. And of course, there would be a point where we reach 10 to the minus 22 EV, so the mass range favored by fuzzy dark matter. But here we're not making any assumptions on the cosmological nature of these particles. Yes. So the idea is that clusters of galaxies allow us to get very tight constraints on G, because we are further down in the y-axis in the low mass range. So this is what I'll be talking about next. So the idea is that galaxy clusters are permeated by the intercluster medium, which is hot gas that is in hydrostatic equilibrium with the dark matter potential wells that are dominating the mass distribution of these clusters. And the ICM is magnetized, and we have evidence of this from Faraday rotation measure observations and synchrotron observations taken in the radio band. So the idea is that if a galaxy cluster is hosting an active galaxy that is very luminous in the X-rays, as the AGN photons are traveling through the magnetized intercluster medium, then this photon axion mixing process should take place. And we should see this as energy dependent modulations appearing in the spectra of these AGN, provided that we have good enough models that are modeling the intercluster medium magnetic field, then we should be able to use this to constrain axions. And the type of field strength that we have in the ICM in the richest clusters, in the inner regions of richest clusters, reach tens of microgauss. And we have, we believe that cluster field strengths should be coherent within tens of kiloparsecs. And we also know that Faraday rotation measure observations of cool core clusters, namely the Perseus cluster, suggest that the thermal to magnetic pressure ratio, which is this plasma beta, should be constant up to the virial radius of this cluster, of cool core clusters. And now I'll be introducing the constraints that we found from NGC1275, which is the central AGN within the Perseus cluster of galaxies that Chandra, of course, has studied both in imaging and spectroscopic mode. So in 2020, Chris Reynolds and collaborators found very tight constraints on low mass axions from a 490 kilosecond Chandra transmission grating observation of NGC1275. And these are values of G that were excluded by this study. And in particular, they used field model for the intercluster medium that had been informed by rotation measure observations of the Perseus cluster. And under the assumption that this plasma beta was constant up to the virial radius of the cluster. But however, there was a study that suggested that if the magnetic field configuration that Reynolds 2020 had used, then these bounds on axions would become even 2 orders of magnitude less sensitive to constraining these particles. So when I started my PhD, what we wanted to answer is whether we could use another cluster AGN system to constrain these particles. And the answer is yes. And to do this, we used Chandra observations of H1821+643. So this is a very luminous radioquiet quasar that is at redshift 0.3. And it turns out that the properties of the host cluster were probed by Helen Russell and collaborators in 2010. So here you can see Helen's data, and these are these black data points, and are best fit to the thermal properties of the cluster. So you see the expectations for the thermal and thermal pressure profile and the number density within the cluster. And under the assumption that the plasma beta, so again, that the thermal to magnetic pressure ratio is constant up to the virial radius, then we were able to infer this magnetic field strength for the host cluster. So this is our comparison with the Perseus model that Reynolds 2020 had used. And you can see that in this cluster, we would expect the field strength to be quite large towards the outer regions of the cluster. And this is given by this orange line comparatively to Perseus. And it turns out that this object is particularly interesting because it has been associated with sources of radio emission, in particular a radio halo and an FR type 1 radio structure, which we were able to use so as to double check the assumptions that we made on the magnetic field. And this was a particularly promising source because there had been Chandra observations in 2001 taken with its energy gratings that were able to probe these particles, as I will explain now. So for anyone who's not too familiar with Chandra, this is a schematic of the telescope, and these are these transmission gratings is where these grating arrays that we use are located. And what the gratings allow us to do is that everything that the telescope sees is being dispersed across these grating arrays. So what this enables is a very high quality extraction of the intrinsic AGN emission free from the contamination of the cluster. And as you can see, this is one of the 5 observations that we use. In total, we use 570 kiloseconds. So a lot of exposure time in X-ray speaking terms. And you can see that the AGN is delimited by this green circle. This is the extraction region, and it's incredibly luminous compared to its surroundings. So this is a very luminous object that is promising in this type of study. Okay, thank you. And as you can see here, these is our best fit model for the data. So this is before we started worrying about axion conversion. And each of the colors is representing a different data set that we use for our study. And overall, we were able to infer high quality spectrum free from pileup and cluster contamination. And these are the residuals resulting from fitting the best fit model to the data. So the question was whether photon to axion conversion was able to describe these energy dependent features. So some of these absorption features that we see here. And to do this, we had to build a library of photon axion mixing models across a wide range of axion masses and couplings. And we did this by generating 500 realizations of the turbulent field within the cluster. So for each of these realizations, what we did was to split the cluster line of sight into cells. And each of these cells is a coherence length for the magnetic field. And this was following what Reynolds 2020 had done for NGC1275. And in each of these cells, we allow the direction of the field to be set independently and randomly. And the strength of the magnetic field strength was set from our predictions for the magnetic field profile. And for each of these field realizations, we solved the equations of motions, giving us the mixing probability for a set of axion parameters. So we did this, sorry, I forgot to say something. We did this by using this Axion-Like particle propagation code that James Matthews, who I've been working with since the start of my PhD, developed. So this is one of the projects that we had when using this code. So here, what we're seeing is the survival probability of the photon. So this is essentially 1 minus the mixing probability for a given set of axion parameters. And these black lines are representing the expected survival probability for 2 different field configurations. So you can see that these energy dips that we're getting are actually quite sensitive to the structure of the magnetic field. So this is why it was important to generate 500 realizations of the turbulent cluster field. And what we did was to fit each of these mixing models to the original spectrum, so to our original data. And then we were able to compute how each of these axion models, how good they were in terms of describing the data. So what we did then was to compare the goodness of fit statistic of the astrophysics only model to each of these axion models. And then we marginalized over the magnetic field configurations that we had used. And we were then able to infer the posteriors on axion parameters to set exclusion bounds on these particles. And this is the main product of our work. As you can see, we were able to marginally improve from the predictions of Reynolds 2020. And these currently hold the tightest constraints to date on these very low mass axions. So again, masses less than 10 to the minus 12, 10 to the minus 13 eV. And we know that these results are dominated by systematic uncertainties that are dominated by the assumptions that we made on the magnetic field. But I'm happy to talk more about this later. And you might be wondering what's next. What do we hope to achieve in the near future? So this is what I've been currently been working on, and I've simulated observations of NGC1275 that will be seen with Athena and Axis. And I'll present some of the results now. So as you may know, the Athena X-ray Observatory is the next generation European mission that will be dedicated to the study of the hot and energetic X-ray universe. And it will consist of 2 instruments that will equip Athena with imaging and spectroscopic capabilities. But the one that I want to focus on is the XIFU, which is the integrative unit that will have an unprecedented spectral energy resolution. So as you can see here, this will mean that Athena will be able to see more refined wiggles. So we should be able to test whether these photon axion mixing models are able to describe these energy dependent residuals that might otherwise get smeared out with the lower spectral resolution telescope. And on the other hand, we know that the Advanced X-ray Imaging Satellite, or the AXIS mission, is a probe-class mission that is being proposed following the recommendations of the Decadal Survey. And Chris Reynolds gave a talk here about a week ago presenting this mission. And it ought to be one of the premium angular resolution satellites on the sky in the 2030s. And you can see here where Axis and Athena lie in this graph compared to current missions. And I just want to highlight that Axis should really be somewhere below Chandra in this graph. So what we have done is to analyze or try to answer how Athena and Axis will be able to do in terms of constraining low mass axions with 200 kilosecond observation of NGC1275. So this is again the central engine of the Perseus cluster. And especially with Athena, we have been really trying to see how the effects of calibration will play into this calculation, because as you can see here, the knowledge on calibration might affect the constraints that we would expect, because calibration induces energy-dependent residuals that have to be taken into account when doing this type of axion searches. And these are our preliminary results. So you can see that our current best constraints are represented by these red lines. So these are the results that I presented for 1821+643. And you can see that if we were able to describe the calibration of Athena really well, only with the 200 kilosecond observation, we would be able to tighten the constraints by almost an order of magnitude. So this is exciting and very important for this type of searches. And even then, being conservative in terms of how we consider these calibration effects, Athena will be able to do a very good job. And this also highlights the power of different missions that maybe would have more moderate spectral resolution to constraining axions, which is the case of Axis here, which will be able to tighten the constraints by a factor of 3. And this is exciting because it highlights the power of next generation missions, which are fundamentally different in their setup to constrain these particles. And I just want to highlight that Athena might be able to be complementary to certain lab experiments that will be built in the near future to probe the realm of Axion-like particle dark matter. And just finally, I wanted to highlight the exciting spin constraint that we found for the high mass supermassive black hole at the center of the 1821 galaxy cluster. So this is just a representation of the supermassive black hole spin constraints that we have found with the X-ray reflection techniques. And as you can see, these are probing a wide range of supermassive black hole masses, so almost 5 orders of magnitude in mass here. And we seem to have detected only progradely spinning black holes. So these are black holes that are accreting and the mass falling into the black hole is being prograde with the direction of rotation of these black holes. And of course, this is important because the no-hair theorem of general relativity states that the fundamental numbers that describe astrophysical black holes are its mass and its spin or angular momentum. So this is what I refer to as the dimensionless spin parameter. And As you can see here, we have many data points in the lower mass range, and we seem not to have many spin constraints for higher mass black holes. And this is important because the spin constraints may tell us about the growth history of these black holes as a function of mass. So whether they grow following coherent or incoherent accretion events, and or supermassive black hole mergers. And this is something that has been tested with hydrodynamical simulations of structure formation more recently, and also semi-analytical predictions and numerical models. So this is our spin constraint for 1821 that I studied in a different paper to the one that I've been presenting up to now. But as you can see, this is the only well-defined spin constraint in the higher mass range. And at the 90% confidence level, we used X-ray reflection methods to constrain the spin of this black hole, applied on the Chandra transmission grating data that I talked about at the beginning. But we are excluding highly spinning black holes. And this is something potentially exciting because it might suggest that the spin is decreasing as a function of the mass of these black holes. So this is something that seems to be favoring the notion that these lower mass black holes may be growing following coherent accretion events, and when they reach a certain mass threshold, their spin might be decreasing due to their ongoing growth with supermassive black hole mergers, and or coherent accretion events, which seems to be in line with the numerical models that I was mentioning in the previous slide. So I'm just going to leave it there and take any questions, and thank you for your attention.
All right, so we'll first take any questions from our in-person audience. All right, go ahead.
Yeah, so you mentioned that when you try to put constraint on the axion coupling constant, you mentioned at some point you had a 500 different magnetic field model. I just don't have a feel for whether that's big enough, or what if you have 5,000? Well, it doesn't depend that much, or how does it work?
Yeah, so one of our collaborators, which is David Marsh in Sweden, did some conversion studies. And we know that if we had considered 200 realizations of the field, our results would be accurate enough. So 500 is a good number for this type of searches. Yeah.
In the back.
Yeah, fascinating talk. I just wanted to ask about the wiggles that you're searching for in terms of the deficit.
Yeah.
Is the narrowness of those features driven by the turbulent scale that you're simulating, or what sets that? And the reason I'm asking is wondering if you would do better going for generally larger collecting area versus finer energy resolution to detect those features.
Yeah, I mean, thank you for your question. I think it's very, like, it's not immediately obvious. I would have to think, because it depends on the type of source that you're looking at. As you can see in the, not this one, sorry. This one, you can see that the constraints that we get at these masses, also like topology varies between the constraints from NGC1275 and 1821. So it depends on the host cluster and the specific source that you're looking at as well. I think with Axis, we've seen that if we have a high collecting area telescope and we are able to filter out the cluster emission, which is something that we won't have with Athena, then the prospects are really exciting and encouraging. And I mean, if we were able to filter out the cluster emission and have something that has very unprecedented spectral resolution, I think this will be key for luminous enough sources, the magnetic field structure of which we know enough about. I have to think more about the question about the turbulence scale, about the magnetic field. Something that I haven't had the chance to mention is that we know that if we were to use a 3-dimensional field structure, so using full MHD and not using these sort of simplified magnetic field models, we will be able to see higher mixing probabilities that we cannot see with these simplified field models. So we think we are being conservative in some way.
Question over here?
Can you go back one slide?
Yeah.
Data? Yeah, so I'm not 100% sure I understood, but if I understood right, you're ruling out these wiggly models because the data is smooth, basically, right? Or
I mean, this is only for a specific type of axion.
right.
So a certain mass and coupling, and here what you can see in but yeah, these values are excluded by the theory.
Okay, so what is it that's setting the energies of the wiggles and the black lines, and are they different? Like the dashed and solid, are those two different energies or two different realizations of turbulence? Or
Yeah, so different realizations of turbulence. So with each of these realizations, we are able to recover the expected magnetic field profile, but the direction of the field within each of these steps over which the magnetic field is coherent will change in each of these realizations.
okay.
Yeah.
Very interesting. I wondered if people had looked at things, systems other than clusters, like pulsars have huge magnetic fields,
Yeah.
although the distances are very small. The product, I think, back at the top of my head, you can actually win by going to a magnetar.
Yes, I think there have been some studies in magnetars. I cannot speak about these because I'm not fully sure about the magnetar, but I know that, for example, you can look at neutron stars, isolated neutron stars, and you would expect axions to be produced at the core of neutron stars because axions and neutrons still mix if you have high enough highly dense mediums. And then you would expect these axions to escape the stellar surface and then reconvert resonantly back into photons once they hit the neutron star magnetosphere. And here we're talking about field strengths, orders and orders of magnitude greater than micro Gauss. And then you can still consider the probability of some of these photons converting back into axions as they propagate through the galactic magnetic fields between the neutron stars and the observer. So yeah, I mean, people are looking at, or people have looked at other sources that can give you higher magnetic fields within a more confined region of parameter space. And presumably with this type of searches, you can access different masses that we are not sensitive to constraining with clusters.
Other questions from our in-person audience? All right, let's check with our online audience. I don't see any questions or anything in the chat. So if there's nothing else, let's thank our speaker for that great talk again.